Hello, hello, hello. In this worked example, I'm going to show you how we can use the Jones vectors and matrices formalism that was described in the polarization tutorial to treat a simple problem. The problem is what happens when you send a vertically polarized light beam into a linear polarizer whose transmission axis is oriented at an angle of plus 45 degrees relative to horizontal. Although this problem is a problem purely in classical physics, as you'll see as the term progresses, there's a lot of what we're doing here that is going to pave the way for the way we deal with polarization states of photons and how to manipulate them in a quantum mechanical treatment. So the basic idea is that there are these things called Jones vectors, normalized vectors that represent the polarization state of a light beam. And the components of the Jones vectors are in general complex numbers. And we can use we can represent the effect that different optical elements like a linear polarizer have on the polarization state by multiplying a Jones matrix, that's this guy here, times the original polarization state, the original polarization Jones vector, and just by multiplying by a matrix, you can calculate the polarization of the outgoing beam. And this example serves to highlight how the mathematics that we're going to deal with a lot this term is the mathematics of linear algebra. So we're told that the input polarization is a vertically polarized beam, and that is going to be represented by, that's one of the two basis states. So the input polarization is just going to be represented by this column vector, a 0 and a 1. And then to calculate the Jones matrix appropriate to this problem, we're going to consult this table that appeared in the polarization tutorial. So different optical elements in this table have different Jones matrices, and we're interested in the effect of a linear polarizer. And so the Jones matrix is given by this 2 by 2 matrix here. And since our linear polarizer is oriented at an angle of plus 45 degrees, all we have to do is plug in the angle theta equal plus 45 in this matrix to calculate the appropriate Jones matrix. And that's easy to do. The cosine of 45 degrees and the sine of 45 degrees are both 1 over the square root of 2. So you can pretty easily see that each element of this 2 by 2 matrix is going to end up being equal to 1/2. So this is what our matrix M looks like. And now we can just calculate the output polarization Jones vector is just given by multiplying 1/2, 1/2, 1/2, 1/2 times 0, 1. And that's going to give us a vector, a column vector, which is just 1/2, 1/2. And you'll notice that that's not a normalized vector. It has a length that's not equal to 1. I can rewrite this as 1 over the square root of 2 times a vector, which is 1 over the square root of 2, 1 over the square root of 2. And this vector here we recognize as the Jones vector associated with a polarization that's at plus 45 degrees above horizontal. So I can write, and this is a totally unsurprising result, that the output polarization is proportional to a polarization state that is at plus 45 degrees. That's what a linear polarizer does. When the beam comes out, it's going to be polarized at plus 45 degrees. But how then are we to interpret this factor of 1 over the square root of 2? So the output vector, Jones vector, is less than 1 unit in length. And that's a manifestation of the fact that the linear polarizer is going to absorb some energy from the light beam. And this 1 over the square root of 2 just reflects the fact that the intensity of the output beam, in this case, is going to be reduced from the intensity of the input beam. So this is our final answer. And that's it for this worked example. Hope to see you again soon. Bye bye.